Have you ever wondered what actually happens if you fall into a black hole? The answer is incredibly strange. What happens entirely depends on who is holding the camera. Imagine two people in this experiment. There is you, sitting safely in a spaceship parked millions of miles away. And there is your friend, who draws the short straw and takes a free-fall dive straight toward the black hole. To understand what happens next, we have to look at a rule Albert Einstein laid out over a century ago. Massive objects warp the space around them, and that intense gravity actually slows down the passage of time. A black hole has a boundary called the event horizon. It is the absolute point of no return. Here, gravity is so intense that not even light can escape, and that time warping effect reaches its absolute extreme. Because time breaks down like this near the edge, a single event splits. The reality of what happens to your falling friend divides into two completely different stories. And surprisingly, both of them are correct. Let's start with your perspective, watching from the safety of the distant spaceship. You are peering through your telescope as your friend gets closer and closer to the darkness. This animation shows what you would see. On your ship, your clock ticks away normally, 1 second per second. But because of that extreme gravity, your friend appears to be moving in slow motion. Their clock stretches out, taking 5 seconds, then 10 seconds, just to tick once. As they reach the exact edge, the event horizon, that extreme effect reaches infinity. From your point of view, your friend's clock grinds to a complete stop. They never actually cross the threshold. Instead, the intense gravity stretches the light coming off their spacesuit. Their image turns a deep, dark red, and they slowly fade away until your telescope cannot detect them at all. To you, and to the entire outside universe, your friend never falls inside. They become a ghost, permanently suspended at the edge of the void. Now, let's switch the camera. We're going to look at the exact same fall, but this time through the eyes of your friend. As they plummet toward the black hole, they do not feel sluggish. Their watch ticks at a perfectly normal rhythm. To them, their local passage of time feels like any other Tuesday. When they cross the event horizon, there is no physical bump. There is no edge or barrier to brush up against. It is just empty space. In a matter of minutes, they drift quietly across the line of no return. This is not a trick of the light or a simple optical illusion. The math of general relativity demands that your frozen outside view and their smooth inside view are both entirely physically real in their own environments. The math perfectly supports this split reality. It allows your friend to drift peacefully across the boundary without a scratch. At least, that was the story until another branch of physics raised an objection. The peaceful crossing falls apart when we bring in quantum mechanics, the set of rules that governs the tiny particles making up the universe. Quantum mechanics has a strict law. The data that makes up a physical object cannot be permanently lost, and it cannot be magically duplicated. When a black hole slowly leaks radiation over time, it creates a mathematical paradox if a person is also falling inside with their own physical data. To fix this, physicists proposed a startling solution. The event horizon isn't empty space. It's an invisible wall of intensely hot particles, a firewall. If it exists, the consequences are violent. Your friend wouldn't drift smoothly. They'd hit this blazing barrier and burn to a crisp. This leaves physics trapped in a brutal contradiction. Your friend is either floating peacefully through empty space, or they are instantly vaporized. It is mathematically impossible for both to be true at once. This is a massive crisis in modern science. It pits the laws of gravity directly against the laws of quantum particles, forcing us to admit that one of our two best frameworks for understanding reality has a major flaw. Scientists cannot solve this with chalkboards alone. This photograph shows the first direct image of a black hole ever captured. Researchers study the glowing rings around these massive structures in deep space to try and find physical evidence of what actually sits at the edge. The debate continues in universities and observatories all over the world. To finally know whether the fall is smooth or fatal, we will need a completely new set of equations, a unifying theory of quantum gravity that brings both sets of rules together. Until we find that missing piece, the edge of a black hole remains the ultimate unsolved cosmic mystery.
It is the one place in the universe where our understanding of reality breaks down completely.